Okay, so finally we're going to look at nuclear fusion. So fission is where a nucleus splits into two smaller nuclei or daughter nuclei. Nuclear fusion is where we have nuclei joining. So nuclear fission is big nuclei splitting into smaller and releasing energy. Nuclear fusion is small nuclei of very light elements joining together, and when they join together they release energy as well. So nuclear fusion is what happens inside the sun and stars. Inside stars, small nuclei join together, they get forced together by the immense gravitational fields that we have inside the star. Temperature as well gives them enough energy to get the nuclei close enough together for fusion to happen. And when they join together, the small nuclei, to make a larger one, energy is released. Now, for that to happen, for example in the sun, our star in our solar system, the temperature is about 15 million degrees Celsius. At that temperature, the hydrogen nuclei are fusing together to form helium nuclei, and in the process releasing vast amounts of energy. This is what happens in stars, but we're also investigating and studying how we can get this to happen, this process to happen here on Earth. And if we can do that, we should be able to harness the energy that's being released to produce electricity. So, how are we trying to get this to happen here on Earth? Okay, nuclear fusion, we could use it as an energy source to run power stations, produce electrical energy, and we would do that by joining hydrogen atoms together to make helium. So in the first stage, when we do this in the fusion reactor, we would be taking two isotopes of hydrogen, okay, which we would take deuterium, which is 1 proton and 1 neutron, and tritium, which is 1 proton and 2 neutrons. Okay, both of these are hydrogen because they only have 1 proton, and the atomic number for hydrogen is 1. These nuclei fuse together to make helium, which is 2 protons and 2 neutrons, and releases extra neutron, which will take away, that neutron will fly off with a large amount of the energy that is released in the reaction. So, deuterium and tritium fusing together to make helium and a neutron, and in the process energy is released in the form of kinetic energy or thermal energy here. Now, to get that to happen, we need very, very, very high pressure to push these nuclei together, close together. We need very high temperatures. We need to give them enough energy to overcome the fact that we have positive charge and positive charge, so these two are going to repel. We have to overcome this electrostatic force to get them close enough together to fuse. Now, it's very difficult to produce these conditions here on Earth because the temperature is extremely high, pressures need to be extremely high, and the question is, how do we, number one, contain all of that, and number two, how do we keep it all stable? There's a number of different fusion reactors running and being tested around the world, none of which are being run commercially to produce electricity, but we will be producing electricity from hydrogen, tritium and deuterium, which we can get out of water. We find that in seawater, these isotopes. And we will be producing helium and neutrons, which is not radioactive for thousands of years, doesn't pollute, so it will give us a way to produce electricity without global warming or without long-lived radioactive waste. This is JET in Oxfordshire in the UK. This is the reactor, which looks a bit like a donut shape. To get it to fusion to happen here on Earth, because we don't have the gravitational field bringing everything together, we need to get even hotter than the sun, about 6 times hotter than what the temperature in the sun's core. So these reactors use magnetic fields to trap very, very hot hydrogen, which has lost, the atoms have lost their electrons and turned into what we call plasma. Okay, which is ionized gas. That can be contained using magnetic fields because it's charged, and we find the easiest way of doing it is like a donut shape or tokamak. So here we've got the reactor body. So what would happen is we would use the heat generated in this fusion reactant to warm up water. The heat from that water will be passed on through a heat exchanger. Here we go, to water that would be turned into steam to run a turbine and run a generator. So exactly the same as all the other ways of producing electricity. Okay, that we have really on Earth, just like fossil fuels and fission nuclear power stations. Except very, very clean because we don't produce long-lived radioactive waste, and we have a cheap, easy source of getting the fuel for it, and helium is not dangerous. And hopefully these will be ready in the next 30 years. So the fuel is abundant in the seawater. We only need a small amount. For example, 10 grams of deuterium and 15 grams of tritium could produce enough energy for a lifetime of an average person in an industrialised country. Clean, no polluting gases or put into the atmosphere. It's safe. We know there's no chain reaction that we need to keep under control. The radioactive waste is less waste. Only the chamber itself will become radioactive, and that will be used for a long time. And we don't produce any waste products that could be turned into nuclear weapons, which is what happens with fission reactors. Okay, so you have a Google Doc to finish off there and put some notes in, two tables.